Welcome, this is Dr. Ali Mugebel. Today we're going to cover characteristic and moment generating functions. Here is the outline that we have been going through, and today specifically we'll focus on the function that gives moment, which are the characteristic function and the moment generating function. Here is the sublist that we would like to cover, characteristic function and the moment generating function. We'll touch on the Chernoff inequality bound. Recall the moments that we had before. So we have two types of moments. Quickly, the nth moment about the origin is defined to be the expected value of x raised to power n. And we also can have a special formula for the case of discrete random variable. For the central moments, the only difference is that we are looking at mu's, which are the expected values of x minus x bar. We are taking things around the central point, which is the mean here. So we have again an equation for the continuous example or the general case, and then also we developed equation for or formula for the special case of being discrete. Now we ask ourselves, is there a way to find the moments, first, second, third? And this is the title of today's lecture. Functions that give moments. We will start with the characteristic function. The characteristic function is defined to be, it's the expected value of not x raised to power n, it's rather the expected value of eta j omega x. And it's defined to be phi, capital Phi of x, where x is the random variable, and it's always function of omega. Again, it's the expected value of the exponential. We'll see why this is relevant. If you find the expected value of this exponent, you get minus infinity to plus infinity, the PDF eta j omega x. Now, what this reminds you with, you might have seen something like this before. If we have a time function here, this is like the Fourier transform, except that there is not a minus sign here. So we can say that the characteristic function, it's like the Fourier transform of omega. The only difference is that there is no minus sign here. And remember, if you have a time function, you can say a lot from its representation in the frequency domain, and you can go, in most of cases, you can go back and forth from time to frequency and so on. So it seems that we came up with another representation of the random variable other than the PDF, which we call the characteristic function, because it carries the characteristics of this random variable. In a similar way, now we can do the inverse Fourier transform. We can get the PDF from the characteristic function. So it contains all the characters of the random variable. If you compare the two formula, just note that there is a minus sign here to go in the inverse direction, the inverse Fourier transform if you like, or inverse from PDF to characteristic function. And note that if you are using omega, you get a 1 over 2 pi here for the differential. Recall that omega equals to nothing but omega equal to 2 by f. So now if you take the differential, d omega equal to 2 by f, 2 by df, and then from there we get this factor. Okay, so we can also show that the magnitude of this characteristic function is always less than or equal to the integral of the individual magnitudes of the multiplied function in the middle. We can use this mathematical property. So then, what is the magnitude of the exponential? This is a complex exponential, so the magnitude here is 1, and this is just a phase, so it's always going to be 1. This is 1. And the PDF is always positive quantity, so this absolute value or amplitude absolute value will just disappear. We get the area of the PDF, which is nothing but 1. So we can say that the characteristic function is always less than or equal to 1. And this one occurs when omega equal to 0. If you substitute omega equal to 0 here, you get the area under the PDF, which is 1. So we can say a very important property here, that the maximum magnitude of the characteristic function is unity, and it occurs at omega equal to 0. Now, why do we go from, we have the PDF, why aren't we happy with the PDF? Why do we have another function? This is called a moment generating function. We notice that if you take the nth derivative of phi of x, what do you get? If you differentiate this in time, you get, this is not function of omega, if you differentiate with respect to omega. So this remains as is. Then the differential here will be the exponent you multiply by jx raised to power n. N is the number of times you take the derivative. Now I can take the n outside. What remains is the integration of fx times xn, which is nothing but, of course, if you put omega equal to 0, this is going to disappear. And then we get this integral, which is nothing but the moment. So this is the nth moment. So in fact, if we differentiate the characteristic function in time, and then we substitute omega equal to 0, what we get is something related to the nth moment. So we can use this to find the moment. We can say the mth moment. Now we can divide both sides by j raised to the power n. You get minus j raised to the power n, the nth derivative of the characteristic function, and then you equate that to 0. Okay, I'll summarize this slide. We have defined the characteristic function, and with this formula we can find the nth moment of the random variable by first taking the nth derivative and then substitute omega equal to 0, scale by minus j raised to the power n, and you get your moment. Now remember that before we used to find the moments by integration, and now it's usually easier to find the derivative given the characteristic function. But there is an issue of will this exist or not. Function that gives moment. We have seen the characteristic function. Now we look at the moment generating function. They are almost the same. If you look at the definition of the moment generating function, there we use phi, here we use capital M. There we use omega, here we'll call it just nu or v if you like. So again, the moment generating function, it's the expected value of exponential vx. We have removed the j and omega and replaced that with v. Why? Maybe just for convenience. Let's see. So here is the definition of the moment generating function. Both of them are moment generating functions, but this is called the moment generating function in short. And then, of course, if you differentiate this function now, there's no issue of j here. You get x raised to the power n, differential. Now substitute v equal to 0 or nu equal to 0, and then this is going to disappear. I'll get the nth moment directly. So it sounds like we got rid of the problem of having j. The nth moment is directly the differentiation and then substituting v equal to 0. In the next slide, we'll apply this to the exponential distribution. So it says here, we will start with the exponential and would like to get the moment generating function. Okay, we deal with the exponential because exponential is easy to integrate and differentiate. Okay, so here we record the example. The characteristic function for exponential distribution is given by the following. Okay, and we want to show that the characteristic function will be given by the following expression. By definition, we look at the expected value of e to j omega x. And then, of course, we multiply this by that. Our integration limit will start from a to infinity, because this term will force everything before a equal to 0 to 0. Now we're just kind of arranging the exponents. So we take things that are not function of x outside the integral, which turns out to be minus with minus plus. So we get exponential a to the ab. 1 over b comes from here. Now we have two exponents, this one in blue, and the remaining here minus x over b. X is a common factor outside. This will make it maybe easier to integrate because we got everything that's not function of x outside. Integration of exponential. Remember that the variable is x, so it's not difficult to integrate. We just divide by the exponent, which what we have done here, and then we substitute the limit. When we substitute the limit, we get, of course, when it's infinity, you get 0, and then you have minus of minus sign. And we got the following expression. Instead of a, we put x, we'll put a. So this is almost the same expression here. With a minus sign, this is going to disappear because we'll start with infinity and that will give you 0. Then minus the substitution of the row limit, we got this expression. A little bit of math, organizing the exponents. I will get these things to cancel, and I got finally the following expression. What do you call this? The characteristic function. Now, it would be logical to use this as an example to find the mean or to find the first moment. If you differentiate, now we have a quotient, we have the differentiate, you differentiate the numerator, okay, multiplied by the denominator, plus the derivative of the numerator, then we get minus the derivative of the denominator, which is jp, And then of course we multiply by the numerator. Of course, divide by the denominator squared. This is something that you're already familiar with. And I got the following expression. So again, if we simplify this expression and substitute for our omega to be 0, multiply by minus j, this comes from the formula for the moments from the characteristic function. And then we solve for m. To put omega equal to 0, these are going to cancel. Things would become much simpler. And then multiply by minus j, I will get a plus b, which is something known for the exponential distribution. We can also practice with the moment generating function for the exponential distribution. So if you want, you can pause the video and try it with the moment generating function. Find the moment generating function and the first moment for the exponential distribution. It's very similar to the previous one. It's much easier because we have no j omega. Just replace it with v. So we got the following expression for the moment generating function. And then if you differentiate, substitute v equal to 0, on u equal to 0, and then of course there is no j here, you get again, of course, you expect to get the same answer. If you want to practice more, you can find the characteristic function for the uniform distribution between a and b. Although uniform is simple and easy, but you will find out that once you start executing the integration, that there is an existence problem, and you might not be able to find the first moment through the characteristic function. So this is just to point out that once you go to differentiation, integration, then you might not be able to do it all the time. Okay, so we may conclude this lecture with the following slide. This is just to complete the picture with the book. We have the Chernoff inequality bound. The Chernoff inequality bound, it says that the probability of being above a certain number is bounded. We can use the moment generating function to find a bound for the probability. And of course, you can go over the derivative, how that this exponential is always going to be greater than this unit step function. And then of course, you can find the probability, the left hand side, by integration from a to infinity, which is nothing but an integration from minus infinity to infinity scaled by the unit step function. And then of course, we can go back to this expression. So I leave this for you to look at. It's just to be exposed to. If somebody says the Chernoff inequality bound, we have seen the Markov inequality before, and the Chebyshev inequality bound to find the probability using only mean and mean and variance. And now, if somebody also having the moment generating function, we can have a bound on the probability. So if this is given, we know what it means. It allows you to find the probability for a given moment generating function. As I said, this is for you to look at. Thank you very much. We'll see you on the coming video.